Okay, so we are continuing our recitation sessions for the, see where I can find the, here we go, from before. So we're looking now at, I want to spend some time today looking at parametric surfaces. And this tends to be the part of the course that students have the most difficulty with. And given that students have the most difficulty with this, I wanted to spend some extra time today looking at these surfaces. And unfortunately, this is the kind of thing where pretty much everything we do for the remainder of the semester is going to use this principle. You know, this principle of parametric surfaces and what these things are. So I wanted to do some examples of these to get a better sense of them, and also look at some other types of parametric surfaces to begin getting a little bit more used to how to work with these things. So what are parametric surfaces? Well, I like to think of them in two different ways, which are not exclusive, but there are two different ways that you can think about them. So on the one hand, you can think about parametric surfaces as kind of like a description of points. So for example, you could have some function which we usually denote by r of u and v, and r u v equals some function f u v I plus g u v j plus h u v k. And u and v are is some point in this domain D, and D is some region in R2. And we say that that function parameterizes that surface if for every point xyz on the surface, there's some point uv in D, so that x is f of uv, y is g of uv, z is h of uv. Now that might sound obvious, but it's easy to lose track of that basic fact when trying to think a little bit more about how to actually parameterize surfaces and actually think about these things. And functionally, what they really are, though, is that this parameterization gives us a way to coordinatize the surface. And in fact, a lot of people who actually study and do research in mathematics really do call parameterizations coordinates for the surface. We actually do think about these things as real coordinates for a surface. So you can think about these in two different ways. And I think about them in both ways, basically. So let's look at an example of this. Suppose we want to identify this surface. We're calling it u squared I plus u cosine vj plus u sine vk. So what this really means, can I get rid of this thumbnail thing on the, before I do this, just want to see if I can get rid of this thumbnail thing on the side to make it a little bit better to I can't seem to get rid of the thumbnails, so whatever, I'm just stuck with those. Okay, fine. So so what this means is that you've got x is equal to u squared, y is equal to u cosine v, and z is equal to u sine v. And one thing that we can do automatically, now you might look at that and say, okay, well, what kind of surface is this? What does this actually look like? Well, one thing we notice is that you've got u cosine v and u sine v for y and z, and that kind of suggests it might not be a bad idea to try actually figuring out what happens when you square those things. So for example, if you take y squared plus z squared, well, that's going to give you u squared cosine v plus u squared sine v, or in other words, u squared. Wait a second, u squared, that's x. We know that that's x. Aha. So in fact, what this really is x equals y squared plus z squared. Now this is taking advantage of the fact that now this is just taking advantage of the fact that we know that x is u squared, y is u cosine v, z is u sine v. So for every point x, y, z, it has to satisfy those three equations. But that implies that they also have to satisfy x equals y squared plus z squared. So in fact, this is what the surface is. This is what that surface will actually give us. X equals y squared plus z squared. And we know what that is. That is an elliptic paraboloid it's an elliptic paraboloid that's centered along the x-axis. By the way, I don't know if Joe showed you guys this before, but I'm going to show it to you now. I'm going to switch my share for a second and go to, let me just give you 1 second. Because I'm going to show you a kind of a nifty way to actually figure out what these things look like. Okay, so now, here we go. So now we're in GeoGebra, and what did we just find? We just found, let me actually just get rid of this stupid plane because I don't like that plane. I don't know why they show us that plane. But what did we do last time? Last time, what we saw just now was that we were looking at the surface that was given by x equals y squared plus z squared, and we see that it's this elliptic paraboloid centered along the x-axis. Remember, the red axis is the x-axis. Now, here's a cool thing you can do with GeoGebra. Suppose I want to create a parametric surface. Well, here's how you do that. You type in surface, and in this case, our surface had the x-coordinate u squared. Our y-coordinate was u times cosine v. Our z-coordinate was u times sine v. And let's say that we've got u going from 0 to 10 and v going from 0 to 2 pi. Aha, that's also a surface. And you see what you get are you get the grid lines for it. You can actually see what the grid lines are for that surface. And that's what the surface is if you think about it as a parametric surface. But at the same time, let me just get rid of this, that's the exact same surface that we found as x equals y squared plus z squared. So this is a handy little way to check your work, to make sure that your surfaces are the same way. This is how you can, if you're doing your homework and you want to use GeoGebra to check yourself and to look at what other surfaces look like and experiment a little bit, this is how you can do that. You can use GeoGebra to create parametric surfaces, and this is how. And we'll do a couple more examples of that during today's recitation. All right, so let's do this example. Here we've got, we want to find parametric equations for the plane that passes through the point 0, -1, 5, and contains the vectors 2, 1, 4, and -3, 2, 5. So how do we parameterize planes? Well, I want to remind everyone how you do that. So the standard way of doing this, if you want to parameterize a plane, you use the following trick. You're going to use the parameterization R of u and v is equal to R naught plus u times, I can't use v, can I? I'm going to use a, vector a, plus v times vector b, where a and b are vectors on the plane. And why does this work? Well, the reason this works is, let's say that you've got your plane. Right, here's your plane. And let's say that this is your point. Oh, and I forgot to point this out. And R naught is a point on the plane. And the reason this works is, suppose here's your point R naught. And let's say that this plane we know contains two different vectors. One of them is going to be, I'm going to use different colors to do this. One of them is going to be A, that's an A, and the other of them is going to be B. And we've got another point on this plane, and it's over here. I'm going to call this point R. The gist basically is that you can go along A some length. So you're going to scale A. This is the vector UA. And then you're going to go along the vector B, which I'm going to do in, what color will I use here? I'll use a lighter green. That's the same green. I'll use a darker green. going to go along the vector b meanwhile. And this is the vector vb, assuming these are the same vector. And what we have here in this case is you're going along UA and then along VB, oh, sorry, VB. Now, all the while that that's going on, you still, actually, I'm not even going to say that. Meanwhile, we've got, that's supposed to be an R, by the way. So the idea is, once you've done all of this, you've got this vector going from R naught to R, and that's the vector R minus R naught. So the idea here basically is that R minus R naught, that orange vector going from the point R to the point R naught, which is just R minus R naught, that is the same thing as the vector UA plus the vector, green, plus the vector VB. That's the idea. And to put this another way, remember, if we're interpreting this as for every point on the surface, there's some U and V satisfying the parametric equations. What that means in particular is that R has to be equal to R naught plus UA plus VB, just by adding R naught to both sides. So that's where this comes from. Now, in particular, what that really means is that for us, R of UV is equal to the point, the point we're interested in this case is 0, -1, 5 as the point on the surface, plus U times, now what's A? A is 2, 1, 4 plus V times the vector -3, 2, 5. If you want to write this a little more concisely, you can write this as RUV is equal to 2U minus 3V, -1 plus U plus 2V, 5 plus 4U plus 5V. Okay. So that's great. That's all that this really comes down to, basically. Questions so far on any of this stuff? Now let's try something a little bit different. What if we want to find a parametric representation of this cylinder? It's a cylinder, x squared plus y squared is 4, for values of z between 0 and 1. Again, what we want to keep in mind here is that so the idea is to find functions fuv, guv, and huv so that the points, fuv, guv, huv is always on the surface. Well, the big clue here is the fact that x squared plus y squared equals 4, which in other words means that if we take your function f uv and you square it, plus your function guv, and you square that, you're always going to get the number 4. Now, what two functions, or what function will do something like that? What function does something like that? Where you square, where you add two functions, you square two functions and you add them, and you always get a constant. Seems an awful lot like sines and cosines, doesn't it? So you can say, for example, that f of u and v You can interpret that. I'm going to actually make that u a little more u-like and less a-like. uv. FUV, we can say is, well, in this case, it would have to be 2 times cosine u. And g of uv would have to be 2 sine u. And I can hear you saying in the background, well, wait a minute, but those only depend on u. What about v? Yeah, I'm not claiming that every coordinate depends on both u and v. I'm only claiming that I'm only claiming that the functions have to satisfy the equations, and these will. If you say in that case, if we say in that case that x equals 2 cosine u and y equals 2 sine u for u between 0 and 2 pi, then we sure have that x squared plus y squared is going to be equal to 4. That's not a problem. What about z? What does z have to be? Well, z can be anything. Actually, it doesn't matter what z is, because we're not told anything about z. That's the only function. That's the only equation we're given. So since z has no conditions on it, in fact, z can be pretty much anything. And let's say, for example, that z is going to be just v. And z is going to be v for values of v between 0 and 1. Why is it between 0 and 1? Well, that has to do with this fact that z is between 0 and 1. So v, if z is equal to v, then v has to be between 0 and 1. So that'll do the trick. We can say in that case that r of uv is 2 cosine u I plus 2 sine u j plus v k for u and v in the domain D, and D in this case is going to be the product of the Cartesian product of the intervals. U has to be between 0 and 2 pi, and V has to be between 0 and 1. That's not a cross product, by the way. That's just a Cartesian set product, meaning that the first coordinate is between 0 and 2 pi, and the second coordinate is between 0 and 1. You can, if you want, you can instead write this as x equals 2 cosine u, y equals 2 sine u, z equals v. Both of these expressions tell you the exact same thing. Those are two different ways of giving you the exact same surface. Let me do a quick example in GeoGebra to show you that, yes, in fact, this does work. Let me just switch over for a second. So for example, we can take the surface to be 2 cosine v, 2 sine v, and actually I did that backwards, didn't I? Surface is 2 times cosine u, 2 times sine u, and v. Now u is going from 0 to 2 pi, and v is going from 0 to 1. And that gives us this piece of the cylinder. That's about all there really is to it. So, and if you zoom in, you can see these grid lines, the coordinate lines that are given by this parametrization. More specifically, by the way, what this really is that when you fix u to be constant, what that's really telling you is when you fix u to be constant, well, that means that x and y are constant, and v can change. And we see that, for example, if you say that, I don't know, x and y are both constant, and maybe they're equal to 1 over root 2, 1 over root 2, which is around here, you get this grid line. You get this grid line, which are these vertical lines, because v, the function in that case is just v. Meanwhile, if v is constant, or z is constant, in other words, you get z is some constant number, and you're left with x and y are 2 cosine u, 2 sine u, and that's going to give us one of these rings around here. So That's what these grid lines actually mean. They're really telling you what happens when these coordinates are held constant. Okay, now what if we want to find a vector function that represents this elliptic paraboloid, z equals x squared plus 2y squared? Now, in this case, this is an example of a surface. This is an example of a surface that, that is a function of two of the other variables. So in this case, z is a function of x and y. Now, what do we want? We want that x to be f u v, y to be some function g of u and v, and z to be some function h of u and v. Now, again, that f and that f, g, and h don't all have to depend on both variables. They can depend on only one of them. But probably but almost certainly both variables are going to get involved. So in particular, we notice that z, here's the way this trick works, z we can see is x squared plus 2y squared. But your variables x and y are free, right? They can be anything we want them to be. And if x and y are free, if x and y can be anything we want them to be, well, okay, let's just say that x is u, and y is its own thing, y is v. Well, why didn't you say that x is u and y is u? Well, because if x and y were both u, if they were both the same variable, then that would mean that x and y would be equal to each other, and that's not implied. Nowhere do we know that. We don't know that x and y are the same thing. But we do know that they are independent of anything else, and they're independent of each other. They can be whatever we want them to be as long as they're each their own thing. There's no conditions on them. So x and y are different. So x is u, y is v, and in particular, that means that z is going to be u squared plus 2v squared, right? Because in other words, this is going to come out from x squared plus 2y squared, if that's what x and y are. So that's our parameterization. That's it. And if you don't believe me, we can check this in GeoGebra. So in this case, we would want to type in the surface, which is in this case, the surface is u, v for x and y, and then z is u squared plus 2v squared. And u, let's say, I don't know, u is going from -10 to 10, and v is going from -10 to 10. Voila, we get this elliptic paraboloid, which, by the way, is the same elliptic paraboloid that we would get if we tried typing in z equals x squared plus 2y squared. You see? They're the exact same thing. GeoGebra doesn't quite know what to do with itself when they're right on top of each other like that, but look, if you get rid of one of them and then replace it with the other one, they're the exact same thing. They give you the exact same surface once you go through this whole process. So that does in fact work. Now, here's something else you can do. You can also talk about, for example, you can try finding a vector function that represents the part of the plane that's inside of this cylinder. Now, that's a little bit trickier. Let's try seeing what we can do with what we did last time. Last time we said that, okay, well, z is a function of x and y, and that's great. That's very helpful to us in this case. So in particular, we can say that z is u plus 3, where x is u, and y is v. Y can be anything. There's a small problem with this, and here's the problem. We can do this. That will give us exactly what we want using the z as a function of x and y, or just x in this case. The problem with this is that that's going to give us too much of the plane. And we only want the plane, the part of the plane that's inside this cylinder. So it has to be the plane inside the cylinder. And how might we do that? So how can we ensure that x squared plus y squared is, is less than or equal to 1. Well, here's what we're going to do. We're not going to start there. We're going to start somewhere slightly different. We're going to say that x is u cosine v, and y is u sine v for v. Now, v is going to be between 0 and 2 pi. What about u? U is going to be between 0 and 1. Now, that will ensure that x squared plus y squared is less than or equal to 1. Right? Because in that case, x squared plus y squared is equal to u squared, which we just saw is less than or equal to 1 in that case. But what about z? Well, z has to be x plus 3. So that's easy enough. Z is u cosine v plus 3. So what that gives us at the end of the day is that's a parameterization. RUV is u cosine v I plus u sine v j plus u cosine v plus 3 k. Or if you prefer, x equals u cosine v, y equals u sine v, and z equals u cosine v plus 3. They mean the exact same thing. Either way, we have that u is between 0 and 1, and v is between 0 and 2 pi. That's a parameterization. And we can check it in GeoGebra to see if this works. If we decide to check this in GeoGebra, then let's try this out. We can say, first of all, let's try what we did originally. Originally, we suggested that we would work with a surface u, v, u plus 3 for u, I don't know, going from negative 10 to 10, and v going from negative 10 to 10. The only reason I'm doing negative 10 to 10, by the way, is just to make sure that it's a really big surface. And we see immediately what the problem is. That surface that we get, it's a plane, and there's nothing wrong with that plane except for the fact that it's not inside the cylinder that we want. So instead, what we're going to do is we're going to instead define a new surface, which is going to be u times cosine v, u times sine v, and u times cosine v plus 3 for u going from 0 to 1 and v going from 0 to 2 pi. Aha! Now that gives us a part of the plane that's inside the cylinder. It's a part of the plane that's inside the cylinder from 0 to 1. Let's actually plug in that cylinder. Z equals x squared plus y squared. Oh, sorry, that's not what I wanted at all. Let me try that again. X squared plus y squared equals 1. That was the cylinder that I was looking for. And we see that the plane is perfectly nested inside of that cylinder. That's great. That's a kind of a cool design, actually. I didn't know that GeoGebra would do that. That's kind of nifty. What happens if I get rid of that thing? Now it looks boring again. Well, okay. But let's take for a second. Not what I wanted. So that's the part of the plane that we want. And by the way, that's the same plane that we had before. It's the exact same thing. The only difference is that that whole plane doesn't live inside of that cylinder. Right? That's the issue, is that that plane doesn't live inside of that cylinder. But this part of the plane does. And we parameterized it so that it gets you inside of that cylinder. So there are lots of different ways that you can parameterize different kinds of surfaces. And it's a really good idea to try to give yourself some extra practice with the problems in Stewart on parameterizing different kinds of surfaces. Because, again, this is probably this is the section of the course that is the most challenging for students. And now, personally, I think this is the coolest part of the course because it's because it requires so much creativity and really thinking about what's going on. It requires a lot more sort of big picture understanding. Literally, it's a big picture, but it requires a lot of big ideas and understanding about what's going on. So I really get a big kick out of it because of that, and it requires really think very deeply about what's going on here. But it is quite difficult, and it takes a lot of practice. So you really can't practice too much with this stuff. So and also I hope it's I should take a screenshot of that design and maybe get a tattoo of that or something like that, because that looks pretty cool. Anyways, okay. Now there's one more thing I want to talk about. Now this is not a something that Joe talked about yesterday, but it's another way to parameterize surfaces that I think is worth looking at, because I think this is kind of interesting and a cool way of parameterizing a bigger class of surfaces, and gives you a bit of an idea about, just to reinforce what we're talking about here. And that has to do with these things called surfaces of revolution. Now you saw these in Calc 1. A surface of revolution in principle is a relatively simple object. It's just a surface that you get by taking some curve in the xy plane and rotating that curve around one of the axes. So an example of this is if you take the function y equals fx. Y equals fx, and you rotate that around the x-axis. Now you think for a little bit about what that looks like. Y equals f of x. That's just some function in, I don't have enough space over here to do this. But you can imagine y equals fx, some curve in the xy plane, and you rotate it around the x-axis. Well, you get some surface, and what's its distance from the x-axis? Well, the distance from the x-axis is the value f of x, right? Which means, in particular, the distance from the x-axis is also y squared plus z squared, which means y squared plus z squared equals f of x squared. So that's what generates the surface of revolution. It's the function y squared plus z squared equals f of x squared. The distance from the x-axis is equal to the value of the function. On the other hand, if you want to parameterize that, well, y squared plus z squared, and that's equal to something. Okay, well, the best way of doing that probably is to use sines and cosines. So you can say, for example, that y is f of x cosine theta, and z equals f of x sine of theta. And what about x? Well, x is just x. X is itself. So, so what we're doing here is, again, this comes down to the all this is going to come down to is the value. The value of the function has to be equal to the excuse me. Let me try that again. The point on the surface has to satisfy this equation: y squared plus z squared equals fx squared. Once you have that equation, it's relatively straightforward to just find out what the right parameterization would be. So let's do a concrete example of this. We want to consider the surface, the parametric equations that are generated by rotating this curve y equals sine of x about the x-axis. And what do you get by doing that? Well, let's see for a second. Let me try sketching this thing. Y equals sine of x from 0 to 2 pi. That's a well-known curve, right? Let's say this is pi, and that's 2 pi. And we know exactly what this thing looks like, right? This is the curve. Sine curve. We learned about these way back in preschool. Maybe not preschool, but a long time ago. And the idea is we're going to rotate. I can't animate this in my current interface, but you can imagine rotating this about the x-axis, and that would give us some function, right? So if you rotate this about the x-axis, you're going to get some funny-looking function, right? Or some funny-looking surface, kind of like this sort of beehive-looking thing, I guess. So that's the surface that we're going to end up getting, and a bit poorly drawn, but you see what I'm trying to get at. In this case, again, just for reference, this is the x-axis and this is the y-axis. And that's what happens when you rotate it about the x-axis. In this formulation, the z-axis is poking up out of the page. And what's that going to give you? Well, the grid curve. And what are the grid curves? Well, the grid curves, just to remind you, are what happens when you set them equal to, when you set the parameters to be constant. Now, again, what's the distance from the x-axis up to the surface. This distance, and when I've drawn it this way, maybe you can see what this distance is. That distance, that's just the function itself, right? So in other words, what do we know here? We know that the distance from the x-axis is, in this case, sine of x, or strictly speaking, absolute value of sine of x. Because once you get past pi, sine of x is negative, but all the same, it's positive sine of x. That's the distance from the x-axis. And that just comes from the fact that that's what this curve is. The curve is y equals sine of x. Right? But it's also equal to, but you also know the distance from the x-axis is given by y squared plus z squared. So, sorry, strictly speaking, square root of y squared plus z squared. So the upshot of this is y squared plus z squared is equal to sine squared of x. Now that's not a parameterizing, that's not a parameterization of the surface, but it does give you an idea about what this will end up looking like. You know that every point has to satisfy that equation. Well, if every point satisfies that equation, how can you guarantee that? Well, you can guarantee that by saying that, for example, y can be sine of x times cosine of theta. Z can be sine of x sine of theta. And x can be, well, what's x? X is just x, right? X is just going to be x itself. No problem there. But let's try actually make this into, if we want to make this as u's and v's, if you prefer, you can say x is u, y equals sine u cosine v, z equals sine u sine v. Where we have x is between, or u in this case, is between 0 and 2 pi, and v is also going to be between 0 and 2 pi, because that's rotating the surface all the way around. Oops, sorry. Let's see if this works out. So now recall that what we originally were looking at was the surface that was given by y squared plus z squared equals sine squared, can I do this? Sine squared of x. GeoGebra doesn't like that very much, so it's not going to graph that because GeoGebra is being dumb. So forget that. That's okay. We'll still see if we can make the surface work. So the surface, we remember, was given by u, x is just u, y is sine of u times cosine of v, and z was equal to sine of u, sine of v. Well, now u is going from 0 to 2 pi, and v is going from 0 to 2 pi as well. Voila. There's our, no. Ah, what just happened? Okay. I can't seem to be able to zoom in on just that because GeoGebra is being dumb. But my point is, if you look down the side of it, let me see if I can experiment with this a little bit and try to create a curve that I want. So the curve that I'm interested in is from, actually I'm going to do something else. I'm going to create a parameter or create a slider. How can I do this? I just want to can I create a slider in a nice way? Maybe not. Oh, there it goes. Okay. And I'm going to say that the curve that I'm interested in is given by, now the x coordinate is just going to be t, and the y coordinate is going to be sine of t times cosine k. Let's start with k being 0. Sine of t, sine of k for t going from 0 to 2. 0 to 2 pi. Now, if I get rid of this surface for a second and go upwards, that's just a sine curve, right? I've created a sine curve in the xy plane. Now, I've created a sine curve, and what do we notice? As that sine curve goes around, it's going to rotate and trace out this surface. What surface? The surface that we just found. So that's how we think about surfaces of revolution. They trace out this sort of ant-looking thing. They trace out what the surface should be when you rotate the curve around the x-axis. And you can do a lot of cool stuff with GeoGebra if you know, with a little practice, but that's what this surface of revolution looks like. And what are the grid curves? Well, if you hold u to be constant, if you make u constant, then you get some constant value for x, and then some radius times cosine v, radius times sine of v. That's just a circle, right? When you hold x or u to be constant, you get these circles. When you hold v to be constant, you get these curves, right? You get so v in this case is I'm showing here to be k when I rotate this around, and you see that each of those curves, each of the the other grid curves, all are going to be these sine curves like that. So that's how you parameterize a surface like this. All right, which I think is kind of cool. So there you go. 1 second. So the last example I want to do is another example of this, this principle of surfaces of rotation. Now in this case, the function we're interested in is x equals 1 over y. So I'm going to, I realize that I just did the entire last example in gray, so I'm going to try not to do it this time. Now the function is x equals 1 over y, which looks something like this. And y is greater than 1. So we're left with this looking kind of thing. 1 over y. About the y-axis. Y-axis means we're rotating it in this direction. If this is the x-axis and this is the y-axis, what this means is that we're taking this object and we're rotating it around the y-axis. So we're getting something at the end of the day which is going to look something like this. Obviously very poorly drawn, but we're getting this weird looking thing. Now y is greater than or equal to 1, so let's say we're going to stop here, and beyond that we're not going to really consider anything. Once again, we have to ask ourselves, okay, well, what's the distance from the y-axis? The distance from the axis of rotation, in other words, which is the y-axis, well, we can see what that distance is. It's going to be 1 over y, right? Whatever your value of y is, if y is constant, the distance from it is just going to be 1 over y. As your distance. And that again comes from the fact that we have x equals 1 over y in this case. But it's also equal to x squared plus z squared, square root. So at the end of the day, what we're going to get here is that x squared plus z squared equals 1 over y squared. And from here, it's pretty much the same exact principle. We can say in this case that x is 1 over y cosine of theta. Y equals y. Y is just going to be the same thing as before. And z is going to be 1 over y sine theta. For y between 1 and infinity in this case, and z between 0 and 2 pi. That will do the trick. So that's, so let's see, and this is a very special object, by the way. I think this is, let me actually see something for a second. So let's actually do, see what happens when we do this in GeoGebra. Again. So the surface that we're interested in is, well, it satisfies the equation x squared plus z squared equals 1 over y squared. And again, GeoGebra doesn't seem to like that because it's being dumb. That's okay. I'll parameterize it myself. And to do that, we can create the surface. The x coordinate is given by, I think we want to write 1 over y, sorry, 1 over u times cosine of v. So u, 1 over u sine v. For u going from, I think we said it's going from 1 to, I'll call it 100. And v is going from 0 to 2 pi. And here it is. You get this kind of weird looking funnel thing. This actually is a very famous object. It turns out this is something called Gabriel's horn. And Gabriel's horn is very peculiar because it turns out that it's an object where if you imagine trying to fill up this thing, you fill up the end of it and you fill it up. It has infinite volume, but finite surface area, which means, sorry, no, other way around. Finite surface area. No, I messed that up. Let me try that again. It has infinite surface area, but finite volume, which means that you can fill it up with paint, but you can't paint it, which is weird. You can, it's got infinite volume, I keep screwing that up. Infinite surface area, finite volume. It's a weird little object, fun little thing to play with. So that's called Gabriel's horn. And that's what that looks like. And proving that it is infinite surface area, well, I leave that to you to work out. It's a fun little exercise in surface area stuff, which you know how to do at this point. So take some time doing that. All right, so I'll end there. But thank you, everyone. Hopefully this was informative. And we will pick this up with surface integrals and what you can do with surfaces next week.